Yeah, so 1801 was the double slit light experiment, and 1865 was Maxwell. I said 1870, 1865, so we were just ending the war. All right, questions to hear? A couple other things. Sort of that light as a wave bit. Since the speed of light was considered constant and in a particular medium, so c equals speed of light. If it is a wave, that means that it's going to be frequency times the wavelength. So the bigger the wavelength, the smaller the frequency. So let's just do a quick and dirty example here. So visible light, 600 nanometers is the wavelength of light that we can see. And off the top of my head, 3? I always have to look those up. I can never remember which goes with which one. The speed of light is approximately 3 times 10 to the 8th meters per second. There is an exact number because the powers that be said, all right, we're going to just establish this. The meter is defined based upon the speed of light. And so we can find the frequency, so we have 3 times 10 to the 8th meters per second is equal to the frequency times 600 nano. What's nano?
Negative 9.
10 to the negative 9.
Negative 9. And so my frequency becomes 3 times 10 to the 8th over 6 times 10 to the negative 7th, which is 0.5 times 10 to the 15th, or 5 times 10 to the 14th hertz. So these electric field, magnetic fields creating and destroying each other, constantly creating, they're doing it 5 times 10 to the 14th times a second. Now you can, I've seen internet videos of this, I still have not done it. You can get a sense of the size of microwaves by, you take a chocolate bar, you put it in the microwave, and you put it in for obviously too long, the whole thing's going to melt. Not long enough, you're not going to see it, but supposedly you can get an idea of the size of microwaves with full-size Hershey bar, and you'll start to see parts where it's starting to melt. And I keep wanting to do this, and I never think about it when I'm at the grocery store and have a chance of buying, big size Hershey bars. So if any of you happen to be at the grocery store and thinking about it, and you got a microwave at home, check it out, see if it works.
I think it'd be hard to see with the Faraday cage. That mesh.
Oh yeah, but you put it in there, you open it up, and you should see the melt marks.
Oh.
Worst case scenario is it melts all over the place, and you lick the tray. So watch the tray before you start it.
I saw another experiment with microwave. If we cut a half of a graph, a piece of graph, and we put it in the microwave, and it will create a plasma.
Oh,
If we cut a half of a graph, and we put close together, and we put in the microwave, and it will create a plasma.
so you said graph.
Graph. Great.
Great.
Yeah.
The fruit?
Yeah, fruit.
Oh.
Yeah, sorry.
Cool.
Yeah, in that video,
Yeah,
if
you
it's
can
the
create
same one that I watched,
plasma.
the guy has this paper that changes color when it's heated, and he puts it in the microwave to get an idea of how the waves look.
Right.
And you get like a graphic basically of how the waves are propagating through.
Ah,
I'll see if I can find it.
I appreciate that. Anytime you run across these videos, just send me a link, please. You just can't eat the paper afterwards. That's the downside to that.
Do that or no?
All right. Now, wave also, light also have energy. So just imagine that when we're creating, when we were creating the waves in the hallway with the long coil. Think about the amount of energy it takes to create this with a certain frequency. If I increase the frequency, does it take more energy or less energy?
More energy.
Yeah, it takes more. And so, the same is true with the light, actually. The higher the frequency, the higher the energy. And this was the first thing that Einstein did to make people go, huh, I wonder if he deserves a Nobel Prize. Now, there were actually 4 papers that came out in 1 year, 3 of which should have gotten them Nobel Prizes. This was one of the papers. That the energy of light, and I'm just going to put a little gamma symbol here as a generic symbol for electromagnetic wave, is equal to a constant times the frequency. This is known as Planck's constant. And it's on the order of 10 to the negative 34th joule seconds. Yeah, some of these numbers here, it bugs me, I just don't know them all. 6 point something. Come on, there we go. Planck's constant, 6.63 times 10 to the negative 34th joule seconds. So this light that we just dealt with here, with this frequency right here, let's figure out how much energy it is. And so like energy of one of those would be 5 times 10 to the 14th hertz times 6.63 times 10 to the negative 34th joule seconds.
.315 times 10 to the negative 19.
Units?
Yeah. That seems like very small.
It is very small.
Very
Yeah,
small.
but
Because Planck's constant is extremely small.
if the amount of energy coming from visible light were huge, then we'd be in trouble every time we stepped outside.
So you say like energy from like gamma waves would be higher, obviously.
Yeah.
What's the frequency after the gamma waves?
I have no idea. I have to look it up.
I mean, gamma ray has a higher frequency.
Yeah.
Yeah, it has higher frequency.
I'm pretty sure gamma is higher frequency. So when you look at visible light, the longer the wavelength, the shorter the frequency, the less energy. And so, so if you look at just the classic, even though there's more than 7 colors, but the classic 7 for visible light, this is the lowest energy here. And the highest energy. So ultraviolet, which is beyond violet, is higher energy than infrared.
How does amplitude come into play?
Amplitude in terms of light would be the number of photons
Okay, so.
that are hidden.
Okay.
And this was the big argument for the particle, or back to particles. Light clearly has wave properties to it.
Yeah, it's like
But-
a line thing on the wave.
If you take a surface here and you shine light onto it, if the light has the right amount of energy, it'll eject electrons. And so you just need a detector over here to pick up the electrons that are getting shot off. They found that, and this was one of Einstein's great insights. So as light is coming in, the problem was that if it's a wave, then a greater amplitude should be more energy if it's a wave. So you crank up the light, and if light was not ejecting, that, in other words, the energy created by the light was not enough to eject an electron, turning it up did not eject electrons. And so this sort of really said, wait a second, it's got wave properties, but it can't be completely a wave. So if I'm trying to throw this marker to hit the ceiling, if I just do that, I'm not gonna hit it. Doing it 100 times is still not gonna change that as long as I'm still putting the same amount of energy in it to begin with. Now, if it doesn't eject an electron, then a greater amplitude, in other words, more photons would eject more. And that's known as the photoelectric effect, which I believe you can experiment with by sticking metal in a microwave. I do not recommend it, but I believe that's the photoelectric effect. I could be wrong on that one, and some physicists say they're not quite sure what is causing it, so. Well, that takes us through chapter 33, section 4. Oh, that's right, there's one more thing before we get to the section I really have issues with. All right, so let's talk a little bit about light traveling in a straight line and some of the effects of that. Questions here before I erase? Oh, the order right here, any of you have that plastic, I think it was Fisher Price came out with it with the different colored rings?
Yeah, I know what you're talking about.
Okay. At one point, they made it so that red was on the bottom, red was the biggest one on the bottom, longest wavelength, lowest energy, and then they went in sort of order here. And then at some point, they switched it around. So, but the older ones, and I have no idea why they did that, was actually sort of reinforcing some physics principles there. And then they said, I'm assuming we hate physics, we're not gonna do it that way anymore, we're gonna put red at the top. Or you get a bunch of humanities people sitting around not really caring. Object. Screen. Light source. Instead of freehanding this. All right. So assuming that this mass is not big enough to cause a curvature in space and time, at least not noticeable, without multi-million-dollar equipment. Light travels in a straight line, so I would expect that light is basically, any light within this area right here is going to hit the object and we'll assume absorbed. And then light down here is going to we'll assume that is straight enough. And we'll assume that's close enough. So in essence, what we have here is a shadow. Where light does not that hit, because any light that would have been in within that cone gets blocked. Because light does not get here, this is known as the umbra. And this does assume that our source of light here is a point source. However, the light bulbs that we have are not point sources. They actually have a size to them. If instead we have a light source that has some size to it, so a non-point source of light, and I have my object over here, and I have my screen. Well now, since light's coming from all sides, we can now sort of break this down. So light coming from the top here, and we'll assume that's close enough. But the light's also coming down here. So that's the light cone coming from the top of the light source. And then we can do the same thing with the other part, with the bottom part. Dang it. We'll assume that's straight enough. Beautifully drawn. So we have this spot right here that's basically blocked from any bit of light coming from here is getting blocked in this region. This is known as the umbra. The parts where this section right here and here, where it's getting light from part of it but not getting light from other parts of it, this is known as the penumbra. And of course, we've got a bunch of triangles here. We've got some algebra we can throw into it. We can actually predict the size of our light source based upon the size of the penumbra and umbra. And I know what you're thinking. You're thinking, what are we waiting for? Let's do it. All right. Questions to hear? That was horrible. I'm trying to split it down the middle. So let's assume that there is a line which basically cuts through this, that my light source is perpendicular to this central line. This, from here to here, is 2 times the radius. I'm going to call it radius S for source. So the diameter. This is 2r sub s. Right here, this is 2r sub o for object. And the distance from here to here, we'll call R sub u. And the distance from here to here, we'll call R sub p. Even though the penumbra is not over the whole section, the actual size of the penumbra region here would be the difference between RP and RU. So what I want to do here is establish a coordinate system. So I'm basically going to make my origin right here. There's my origin right there, origin. And so we're just going to come up with equations for these 4 lines here. Let's do it from the point of view of the screen. So this is A, B, C, and D. Those are my 4 major lines. So first let's find the slope of A. So how do you find slope?
Rise over run.
All right. So line A is coming from the bottom here, so it's this point and this point right here. So if I look at that, this point right here, since my origin is right there, this point right here is the point 0, negative R sub s. Using XY coordinates, traditional XY coordinate system. This point right here would be, oh, I need to give some distances there. So I'm going to call this X sub SO. And distance from here, X sub, let's just do OU. So this point right here is, well, in the X direction, we went over X S sub O, or sub SO, and then we went up R sub 0, or R sub O. So that's that point right there. And so my rise, oh, the difference in my y coordinates, so R sub O minus negative R sub S over X sub SO minus 0. That's rise over run, which is RO plus RS over X sub SO. Therefore, the equation of my line darker. This is y equals slope intercept form. The y equals slope x plus b. I know my slope now. What's my intercept?
Negative RS.
Yep. Because this is my y-axis right here. This is my x-axis. So y sub a is equal to r naught plus rs x s sub o minus rs. So I have an x minus r sub s. So I can now figure out, using that equation there, that point right there. All I have to do is put in the right value for x into that equation, and my value for x is that. So that distance up there, that is RU plus RP. No, just RP. So RP equals RO plus RS over XSO times my X value, which is XSO plus XOU minus RS. Let's see, predicting the light source. So basically I want to solve for RS. This is what I want to solve for right here. So let's get some stuff together here. So I have RP. I'm just going to multiply everything by XSO. Just to get rid of my fractions. Equals, now I'm multiplying 2 binomials here. So this is ROXSO plus outer ROXOU plus inner RS XSO plus outer, last RS XOU minus RS XSO. Not pretty looking, it's not like it's gonna come down to something incredibly simple, but at least we can get rid of this and that. Since I'm solving for RS, where's the RS's? I got an RS right there. That's what we're solving for. The radius of the source. And so I get this stuff over, so I have RP XSO minus RO XSO minus RO XOU over RS. Oh, sorry, wrong one. Over XOU equals RS. And so we can now predict the size of a source based upon basically the distance from the center line to the edge of the penumbra. You can go through a similar method for all the others. It's just a question of how much do you love algebra? I mean, besides the normal amount that people love algebra. I'm not sensing the enthusiasm I was expecting here. Algebra. You people are no fun. Or maybe you are, right? I can't tell. All right, so we got just a couple minutes left.
I think my brain's melting.
Pardon?
I think my brain's melting.
That tends to take away from the fun of algebra. That was section 33.4. 33.5 is a difficult chapter for me because it's a bunch of, at least the next several not chapters, but sections are vocabulary that I just don't use on a regular basis. We're still going to go through them. I'm hoping one day it will click and to the point where I will know the stuff and I'll see the term radiant power and I'll immediately know what that means without having to go, wait a second, which one is that? Well, radiant power is actually one of the easier ones. It's the power of what's actually radiated. But then you get into the other vocabulary right now. Luminous flux. I mean, to me, it's not inherent in the term luminous flux what that means, other than luminous means that it is something that you can see. It's bright enough to see. But luminous flux versus luminous intensity. Yeah, I'm looking at the definitions right here, so I could tell you if I needed to at the moment. But the term luminous flux, luminous intensity are not inherently obvious other than we can see it. And so that is one common thread. Luminous means that it is something within the visible spectrum. However, that will wait till Wednesday, probably. Are there any questions before we part ways?
Here, you guys can help me hand it over.
Yeah, I have some. Yeah.
Okay, so you got lab stuff? Yes.
Do we study about the turbulent flux?
Basically like.
Say it again?
Do we study about turbulent flux? So turbulent flux? Yes, turbulent flux.
What?
Yeah,
Theta and rad.
I'm not familiar with turbulent flux.
Theta or sine theta, or the average of the two. So you have three options.
Okay.
Turbulence,
That's pretty much.
no, we're not gonna cover turbulence.
I don't get
Yeah, I'm not familiar with it.
We can't
It's like, there's like 20% at 5, and then it's like 7% at 20.
So the higher you go, the more your angle is more big to the. So also, don't forget about the
Turbulent flux.
So, I'm not be wrong, but right
I think turbulent flux is dealing with air.
Oh, you put on here.
No, we're not dealing with that. That
It's all cracks, right?
would be, or anything probably part of the fluid mechanics course. Yeah, seeing the drawing, I'm thinking, oh, okay, yeah, I dealt with that 40 years ago. But I haven't done that since.
Okay.
Yeah,
Because we have this on video.
Oh, I guess,
no one has.
Yes.
No one can
There's
sell
more we can go.
If you go to the
No.
website, you're in, if you wanna get.
Isn't that one of the $1 million?
Yeah, I mean, I
Yeah, yeah, I
Is
need
it
to
Navy
know.
or Stokes equation?
Yeah, it's, I don't know the name of,
Oh, that is the first quiz I have.
Yeah,
Any
alpha,
answers?
equation.
Yeah, that was,
Oh, yeah, I felt
the
really good
Millennium,
about that.
Millennium
The
Prize?
second,
Yeah.
second question.
Okay, Millennium Prize, okay.
I can,
Maybe I'll tackle it this
Thomas
weekend.
whenever that-
Have a solution by Monday.
And
then retire.
I opened the tab this morning. I didn't go with it, but, I like, that was the first one that I came out with my feeling. What'd you say?
See you on Wednesday.
See you Wednesday, Colin.
Oh, did you get my email about the, lab data? Sent it on Wednesday?
Oh, yes, I did get it. I apologize.
You're fine. I just wanted to make sure.
Yeah, I did see it. Thanks for bringing it back to my attention. If, you can also, it's perfectly fine just to send a follow-up email and say, hey, have you had a chance to
Okay.
think about this?
So-
Preferably that over, where's my data?
Yeah, alright, awesome. I just wanted to make sure that it was still on your radar.
It had fallen off, but it's back on. Thank you.
Alright, sweet.